Greetings, everyone. Time to backtrack a little bit, and we're going to go back to one of the topics that's right on the border of your last calculus course leading into this one, right? Vector functions should have been something you've talked about a little bit in a couple of different classes, and if nothing else, parametric equations for sure, right? So we need to talk about vector functions now because we're going to lead into some calculus that involves actual vector functions. So vector calculus will be right after we're through with these topics. Okay, so just a quick recap. A vector function, much like a parametric equation, takes your coordinates x, y, and z and makes them a function of some other variable. Very often we use t. Some people like to think of it as time, but it's just basically a counter variable that gives you an input other than one of your coordinates being an input. So basically all of your coordinates are controlled there. The difference is parametric equations output points, vector functions output vectors. So the r of t does represent a position, but typically what you'll have is your axes, and the vector will point to some location as a vector from the origin. And then as your position moves, that vector will move around while still originating from the origin. And basically, you'll notice we do only have one independent variable here, in this case t. That does imply that these are only going to be mapping out curves, not surfaces, right? For only one independent variable, so I only have one dimension of freedom. However, I can move all throughout space, but when I say a dimension of freedom, I can only go forward and backward of t, right? Now, of course, along with vector functions, we take derivatives. We would then have a velocity vector and an acceleration vector when we do our first and second derivatives. And then some other aspects of these are actually what we really want to talk about here, okay? So more of the calculus side rather than the physics side. We're going to hit that this is a tangent vector. Of course, it's a derivative. You're going to get a tangent, right? But the vector that you get is going to be pointing in a tangent line direction. So if this is your curve, right, and I pick some point to be whenever t is some value a, right, then the r prime evaluated at a is going to give you some vector that's going to be tangent to the curve at that point, okay? And the vector is just going to point in the direction that the curve is oriented, okay? So if your curve is oriented in the direction where it's going like this, let's say that your t equals 0 is right here, right? Then t equals some value a greater than 0, and the orientation, it would take it along the curve this way. And when you actually get there, the r prime of a is going to give you some vector that is tangent. And that would happen at any point, okay? Then your second derivative, as we've always heard of, is acceleration. Notice I didn't actually label that as any kind of special vector, right? And I know you're thinking that we should lead into some sort of normal vector of some sort, and that is where we're getting there, but you have to remember there's more information than just a size going on here. We've stepped into the world of vectors, and vectors carry two pieces of information at least each, right? They have a direction and a magnitude, and if we're measuring the change, either one of those things could change. So if you're doing a derivative of a vector, then you have a lot of changing information going on, and we have to account for that, okay? So the r double prime, the acceleration, does not necessarily give you a perpendicular vector or a normal vector because it's not always at a right angle to the r prime velocity vector, okay? So it is the acceleration vector. Notice it will be pointing in the direction that the curve is turning, right? Because it's like being pulled that way, but there's more going on there. There's also the change in the velocity, the size of this vector that's changing, not just the pull in the direction with this acceleration vector, okay? So to simplify a lot of those ideas, what we're going to be interested in doing is finding a unit frame for the path at each point, okay? And eventually you'll see we're going to call that the TNB frame, okay? We're get there one step at a time though, okay? So at any particular point, I'm going to find a set of vectors that are unit vectors that talk about the change of the position, velocity, so on and so on, okay, along this path, okay? So let's start with the first one, the unit tangent vector. Straightforward idea here. We already had a tangent vector, so if I divide that vector by his own length, I get a unit vector that's pointing in that same direction, right? So the derivative vector divided by his own length will give me the capital T unit tangent vector that I'm interested in, okay? So the advantages here beyond that are, now that I have a unit vector, I mean, that's nice. I only have to worry about the direction now. It's always going to be length 1. No matter what value of T I put in, the length of that vector will be 1. So it will never change, right? So when I actually do further derivatives, if I perform them on the tangent unit vector, then the only information that can change is the direction. Because it's a unit vector, the length never changes. So the only thing that can change is the direction, okay? So then the next step would be, instead of doing r double prime directly, then what I would be interested in is capital T prime, okay? It is different than what I was saying before. It is actually provable that capital T, the unit tangent vector, is perpendicular, orthogonal to its own derivative, okay? Now think about this for a second. It's a unit vector, right? If a unit vector never changes in size, then the only thing that can change is his direction. Well, that means that if there is any sort of vector that represents the tangent to the tangent, right? It would have to be tangent to it. It's going to have to be perpendicular, because if it's any kind of other angle, it would change the size of the vector, right? So it makes sense that they would have to be at a right angle to each other in order to do just a perfect turn with no change in the length of the unit tangent vector, okay? So the idea that his own derivative is perpendicular to him makes sense, you know, to space. Let's actually prove it also. If I dot the unit tangent vector with itself, then I get 1, which is basically the square of his length. 1 squared is 1, right? Now take a derivative of both sides of that. The derivative of 1 is still 0. And then the derivative of this product rule, of this dot product here is a product rule, which I can perform the standard way, right? Keep one, do the derivative of the other plus the opposite. It's still equal to 0. But these two are the same thing, right? So it's actually 2 times this. And if I divide both sides by 2, what I get is t dotted with t prime is equal to 0. Okay? Well, and remember, if you dot two things and get 0, they're perpendicular. They're orthogonal to each other. Okay? So what does this mean for us? It means that now that I have moved into the unit tangent vector world, now taking a derivative of this new unit tangent vector will give me a normal vector direction, because it will be orthogonal to the original unit tangent vector. Okay, so by taking away the size, making this into a unit tangent vector, it then empowers my derivative to be something that will give me the normal direction that I'm interested in. And that's where we can move to here. Okay, of course we still want to work with a unit vector. So when I take t prime, I get a normal vector, but I want it to be a unit one also. So notice I'm going to divide by his own length also. So after I've taken the derivative of the unit tangent vector, I also find his length and divide it by himself. That will give us what we call the principal unit normal vector. Now be careful, We have to call it the principal unit normal vector because technically there's two normal vectors to any curve. When I'm going along a path here, okay, the normal vector is going to be at a right angle to the tangent vector, but technically there's going to be two of them, right? If I have some tangent vector going some way, the normal vector would be at a right angle to it. But if I do my calculations a little funky, I might get the other one instead by accident. They'll all be in the same plane, but this one won't be the principal unit normal vector. What I want is the principal unit normal vector, which is the one that points in the direction of the curve turning. Okay? And that's actually what we're interested in, right? This normal vector should be measuring a change in the tangent vector. But the only change that I'm interested in is turning, right? Not the size, which is why we went with the unit tangent vector. Okay? So this normal vector is pointing in the direction of the curve because that's the direction that the tangent vector is going to turn, right? If I'm going to have my tangent vector here and it's going to turn, it's going to do this, right? It's going to continue to do that. So that's my second vector in my set of unit vectors at any given point. I've got my unit tangent vector and I've got my unit normal vector now. Okay? Well, one step left to get a third one. We call it the binormal vector. And all we're going to do is we're going to take the cross product of the unit tangent vector with the unit normal vector. Okay? Now, two things. Since t and n are guaranteed to be at right angles to each other, then the angle between them is 90 degrees. And the sine of 90, right? The sine of 90 degrees is 1. And the length of t and n are also both 1. They're unit vectors. Okay? So the size of b comes from the formula with cross product. The size of b is going to be equal to the size of t times the size of n times the sine of the angle between them, t and n. We just said there's a 90-degree angle between them, so this value is going to be 1. And both of these are unit vectors, so those are also 1. So what are we getting at here? Since I've already gone through all the trouble to make the unit tangent vector and the unit normal vector unit vectors, length 1, and orthogonal to each other, then simply doing this cross product will automatically give me a unit vector, something that has size 1. And since it's a cross product, also guaranteed to be at a right angle to the other two vectors. So then that completes the triple. If I create a unit tangent vector, right, take the derivative, divide by that length again, I get a unit normal vector. Cross those two, I get the unit binormal vector. And then the three of those together, we call the TNB frame. Okay? It also is called the Frenet-Serre frame because in differential geometry, the Frenet-Serre apparatus deals with motion along a path and further calculations of that and curvature and things like that. Okay? Now, one other thing that I wanted to mention here is sometimes we'll go through these calculations directly as I've shown you with the formulas here, right? Create the unit tangent vector, take his derivative, divide by his length. Some calculations are smooth that way. Sometimes they're a little bit hair pully, right? So I have also come up with an alternate method for finding the n vector, right? Right here, if you take the derivative vector function and cross product that with the second derivative of the vector function, then take that result and cross product it again back with the first derivative, okay? You'll get a vector. If you divide by that vector's length, it will then also be equivalent to the unit normal vector, the principal unit normal vector, okay? Let's talk about that for just a second. Look at the r prime and the r double prime vectors that I've drawn here. It's just an example, right? Those two are not going to be at a right angle to each other. not all the time, right? It's not guaranteed. So if I cross product r prime and r double prime, right, the result will be something pointing out of the plane of those two vectors, which technically should be in the same direction as B. It will be in the same direction as B, right, because these two have that. Now, if I take the tangent vector and the vector that I've just gotten by crossing those two, right, then I should get something else that's at a right angle to them. Notice what that does is it puts me in the direction of the unit normal vector, right? Because I have these two, that's r prime cross r double prime will give me the one coming out of the board here. So then if I cross it again with this again, I'll get something at a right angle to those two again, right? It goes by the right hand rule there. It's going to have to go this way, right? It's going to cross into it like that. Okay. So by doing these cross products in that order, okay, you're actually going to get the normal direction. Then dividing by his own length makes it a unit vector. And so you get the normal vector this way. Now it seems more complicated, I know, but after a couple of examples, I'll work a couple of them both ways. You'll see some work good one way, some work good another. It just depends on what kind of functions you start with. Okay. Let's take a look at the vector function 1 plus sine pi t, and 1 minus cosine pi t. And what this is a helical path, something that spirals, okay? And the 1 plus right here and the 1 minus right here, all it does is it shifts it a little bit above the plane and over some from this. You can see the way I've drawn it right here, it spirals like this, and it's parallel to the y-axis, right? Y is just going linearly down the way. I dashed it right here so you can see that that's behind that. It just spirals like this, okay? So if you were to look at it down the barrel where the y-axis is coming straight at you right here, right? It would look like a circle in the xz plane, okay? All right, so what I've got to do first to find my TNB frame, right? And then later on we'll find it at a specific point of the curve. So first thing I need is r prime, right? First derivative. That's going to be pi cosine pi t, 1, and pi sine pi t. Okay? All right. Next, I'm going to do my second derivative. Or actually, no, wait. I don't want to do that. I'm going to do his length. Right? The length of r prime there. The length of it. So that's going to be square root of each of the pieces squared. Like so. Good news for us, we're going to have the same coefficients in front of a cosine squared and a sine squared that have the same argument, right? So these two pieces right here are going to add together to give me pi squared. Therefore, the length of my tangent vector is just going to be the square root of pi squared plus 1. Right? Cosine squared plus sine squared, right? But they both have a pi squared in front. And then plus 1. Okay, so my t, my unit tangent vector at some point t is going to be, this is a constant right here. So it's easy enough for me just to write 1 over square root of pi squared plus 1 times the vector pi cosine pi t 1 and pi sine pi t. And all it's doing is it's scaling all of the tangent vectors by this factor, right? It's just some constant scalar there. All right, well next we want to find the n, right? The principal unit normal vector. Okay, so to do that, I'm just going to take a derivative of this tangent vector here. Well, that's easy enough. That's going to be equivalent to just taking the second derivative here, because the vector itself didn't change, right? The vector portion, as far as the direction is concerned, didn't change. I just scaled it. So I'll be taking the derivative of that, right? T prime is going to be equal to 1 over square root pi squared plus 1 times the derivative, right? So that's going to give me pi squared times negative sine, so negative pi squared sine pi t. Derivative of 1 is 0. And then pi squared cosine pi t. Okay? So I took the derivative, right? Multiplied number's still there. Now I want to get the length of that. Okay? Well, here's the good thing about pulling a factor out front of a vector. If you're going to do the length, then it's just the absolute value of this piece, which this is already positive, so it's this, times the length of this. So square root of this squared gives me pi to the 4th sine squared pi t plus pi to the 4th cosine squared pi t. And again, sine squared plus cosine squared, right, gives me the same thing out. And what I end up with in this piece right here is the square root of pi to the 4th, which hopefully is still pi squared. So the length of the derivative vector there, I'm sorry, not the derivative vector, the derivative of the unit tangent vector is going to be pi squared divided by the square root of pi squared plus 1. Okay. So my unit normal vector at any point t is going to be the division of that times the derivative of this. Okay? So to do the division of this, to divide by this length, I'm really just going to multiply by the reciprocal. Pi squared plus 1, pi squared times the derivative of the tangent vector here. So 1 over square root pi squared plus 1. And then I've got negative pi squared sine pi t, 0, and pi squared cosine pi t. Notice these two pieces wipe out, right? So I'm really just left with 1 over pi squared times this vector here, which would make it the unit normal vector, right? Okay, so quick check. Are these two at a right angle to each other? Well, dot them. If I do this times this, I get negative pi cubed sine times cosine, right? Sine pi t, cosine pi t. Here I get pi cubed positive sine pi t, cosine pi t, plus 0. So those add up to 0, then plus 0. They're definitely at a right angle to each other, okay? And we just normalized both of them by dividing by their lengths, so they're definitely both unit vectors. So to finish out for B, right? I just need to cross them. Like this. Okay. So also with determinants, remember what we're going to do here is a determinant. I, J, and K. And I can just pull out the two lengths outside of it there, right? So times 1 over, I got pi squared times the square root of pi squared plus 1. Okay? All right. Now the dotting process, right? This is going to be pi cosine pi t 1 pi sine pi t negative pi squared sine pi t 0 and pi squared cosine pi t. Okay. So I'm doing the cross product there now. I'll bring this out front. Okay. Now, vector time. For the I component, right, I wipe these out, and I've got pi squared cosine pi t minus 0. So pi squared cosine pi t, it is. Next for the j, don't forget it's actually alternating, so I'll have a negative, and then I'll have pi cubed cosine pi t squared plus, because of the double negative, pi cubed sine squared pi t. I'm going to end up with pi cubed. Again, let me go through that. That's giving me a cosine squared plus, because of the double negative, a sine squared. And they both have the same argument, and they both have the same coefficient of pi cubed. So I just get 1 times pi cubed. Right? And then the last portion over here, I'm going to have k. Whoops, I forgot again, didn't I? It should be negative. That one was alternated. Okay, so now for the k, I wipe out these two, and I'm doing 0 minus negative. So I get pi squared sine pi t, like so. Right? And if you check it with either of the other ones, you'll notice that it does indeed zero out with them. Right? So this is my binormal vector at any point t. Okay? So then the only thing left, if you want to, or if you need to talk about a specific point on the curve t equals 3.3 in this case, then all we need to do is plug in for that, right? So when t equals 3.3, right, my tangent vector, my unit tangent vector is going to be, let me go ahead and crunch it, right? So here we go. I'm going to do pi cosine 3.3 pi divided by the square root of pi squared plus 1. Okay, so pi, make sure you're in radians, cosine of pi times 3.3, and then divide by square root pi squared plus 1. Okay, negative 5.6. Okay. Let's see, while I have this punched up, I'll do the z component, because all I have to do is change it to a sine. Negative 0.77. Okay. And then for the last one, I just need 1 over the square root of pi squared plus 1, which is 0.3033. Okay. All right. Oh, looky. I did actually miss this, didn't I? I can actually divide the pi squared out here. So here, let me simplify that a little bit. My n vector, oh yeah, look, I can reduce here too. I can't believe I missed that. My n vector, I can wipe out the pi squareds because 0 over pi squared is still there, right? So it's negative sine pi t, 0 cosine pi t, which makes sense, right? Because the length of that would still be 1. And the only thing that changes is I just forgot to wipe out here as well, which is going to take a pi squared. It's going to make this just pi and wipe that one out, right? Yeah. So it'll just be easier and quicker to plug in is all. The normal vector, right? So just negative sine pi 3.3, 0.81, 0 for the 0, and then change this to cosine, negative 0.59. Should work. Okay. And then my b vector for that particular piece. I'm just going to do, oh yeah, look at that. Okay. So I've got cosine pi times 3.3 divided by square root of pi squared plus 1. Okay, so negative 0.1718. Right? Okay, so let's do the next one here just by changing this to sine. Right? Yep. Okay, so then negative 0.2425. Okay. And lastly, I have negative pi over square root of pi squared plus 1. Negative 0.95. Oh. Okay. Okay, guys. So there's the TNB frame for this curve, and then the TNB frame at a particular point. Why don't you take a look at what this really looks like with the little thing I've designed in GeoGebra now. Here's the parametric representation of that curve. And as I was telling you before, it looks like the helical spiral parallel with the y-axis, and if you look at it in the xz plane, you know, you get a circle. See? It's a circle in the xz plane. So let me pick a point that can be on the shape right here. And that point is going to be controlled by the t value that I have set with this slider right here. Okay? So as you can see, if I set the point in motion, it goes along the path in the oriented fashion that you'd expect. Right? But what you really need to see is what's happening with the Tn and B vectors as this is going on. So let's rewind it back to here again. And let's turn on
the tangent vector, just t for a moment. Now remember, this is the unit tangent vector, okay? And so what you got to remember is that this is always going to be pointing in the direction of the motion of the next placement. So as you can see right now, it's pointing downward. That means that the particle is moving along that path, right? Moving along the path in that direction. And as I let it play out, the tangent vector is always tangent and always pointing in that direction of motion. What about the unit normal vector? Right? Let's rewind again. The unit normal vector, remember, is going to be perpendicular, but it's always going to be pointing in the direction that the curvature should be bending, right? So look, there's the normal vector right there, and you can see that it's pointing with the curve in some aspects, but also the direction that the tangent vector is going to turn is the way that the normal vector should be pointing here. So again, as you see it go on, the normal vector continues to point towards the bend of the curvature of the curve. Okay? Now sometimes you'll see it stick out, but it's always basically, in this case, pointing at the center of the rotation. Okay, let's rewind again. And here, let's throw in B. I know we haven't talked about B much, but look, here's B. So in its current position, you can see B is definitely at a right angle to the other two, right? I've got the TN plane right here, right? And then B is just the perpendicular vector to that. But remember, B is the bivector, the binormal vector. So that's going to basically be pointing in the way that the curve wants to twist. So it's not enough that the point moves along this path. Watch the green B vector and you'll see the actual path has some twisting to it as well. You can see it's not just staying straight pointing backward. See, the B vector is actually canting. It is actually bending. So you have some twist going on there. Okay, and then the point in question that we were asked about was 3.3. T was 3.3. So let's look at that one. That's this location right here. This is the point that we found the TNB frame for, specifically in this case. Right? If we scroll down, you can see here's the B, N, and T vectors just as advertised when we were calculating it. Those are exactly the same, and as they should be.
The next example I want to show you has all polynomial pieces, okay? And you might think, oh, those are going to be a lot easier, right? Because the derivatives of polynomials are pretty straightforward and easy. Yes and no. It depends on how lucky you get. So I have a couple of examples with that. I'm going to show you both ways with this one. I'm going to find the T and N both of the ways that I've described earlier, okay? So let's find, we're just finding the T and N this time, right? Because to find B is just then an exercise in cross product. Okay? So find T and N is what we're going at here. And this particular curve is a non-planar curve, okay? So in other words, I can't just take the whole curve in space and make it fit in one plane, okay? Technically the last one was also a non-planar curve. But this one sort of swirls like a cubic and also like a square root cubed, right? It swirls from up underneath and then does like that, okay? So let's begin. Start with r prime, 2t squared, 1. Okay? So then from here, I would be interested in finding the length of r prime, right? Which is going to be the square root of 2t squared, right? So 4t squared plus 2t squared all squared, so 4t to the fourth, plus 1 squared, which is 1, right? Now it may not look like it, but if you put the 4t to the fourth in front and the 4t squared here, you can actually factor that into 2t squared plus 1 quantity squared, right? Which if I take a square root of a squared, I get an absolute value. Lucky for us, 2t squared plus 1 is always positive anyway. So I can just say 2t squared plus 1 is the length of my tangent vector there. Okay, so then what is t? Right, the unit tangent vector is then 1 over, or everything over, 2t squared plus 1. So 2t squared, 2t squared plus 1, and 1 over 2t squared plus 1. So yes, the length of my tangent vector worked out great. I want you to notice one little piece out of place would have made this, even if it was factorable, maybe not a square factorable, this one actually worked out really nice as far as that part is concerned. But even still, having to divide by it, now I've got some quotient rules to deal with. To make this one a little easier, I'm going to rewrite it by putting a plus 1 and minus 1 in here. And the reason why that works out great is because you'll notice 2t squared plus 1 and 2t squared plus 1, right? I can put that as a 1, and then I still have minus 1 over the 2t squared plus 1, okay? So this middle piece right here, this piece, I am going to rewrite as 1 minus 1 over 2t squared plus 1. And the only reason I do that is it just makes my derivatives a little bit easier, that's all. Okay, so now, derivative of that, well, I'm going to need a quotient rule here, right? So low d high, that's going to give me 4t squared plus 2 minus high d low, that's 2t times 4t, 8t squared over low squared, 2t squared plus 1 squared. Okay, next, derivative of this and this actually comes out to be very similar because the derivative of the 1 part right here is 0. So the derivative here I can do just with a chain rule using the 2t squared plus 1 to the negative 1 power. Okay, so all I'm going to get is 4t over 2t squared plus 1 quantity squared, and over here the negative 4t over 2t squared plus 1 squared. Okay, now if you missed that, real quick recap, all I did was I rewrote 1 over 2t squared plus 1 as 2t squared plus 1 to the negative 1 power. And then I just did a chain rule, right? So you multiply by the negative 1, and you multiply the inside derivative, which is 4t, and it would be to the negative 2 power. And then that worked for both of these. The only difference was, of course, the negative here made that one positive. Okay, so that's all I did here. It was just a quick chain rule. Okay, so then to make my normal vector from this point, I simply need to find the length of this. However, I can make that easier on myself by doing some factoring. I notice that I can rewrite this tangent vector derivative, right? This, I can rewrite this vector right here. They all have the same denominator, right? Oh, and let's simplify this numerator right here, right? This numerator right here is 2 minus 4t squared. Okay, so here's what I notice. All of the pieces have the same denominator. I can factor that out. 2t squared plus 1 squared. Okay? Yeah, it's got a variable. It's okay to factor that out because it's constant for all of them. Right? No matter what value of t, it's the same for all of them. So I can basically call that a scalar by just something with a variable in it. Okay? Also note, I can get a 2 factored out of this, right? And I can also get a 2 factored out of these two as well, right? Okay. So I'm pulling a 2 right here. And that leaves me with the 1 minus 2t squared. And that's it, right? Because I took the denominator out. Let me write it a little bit bigger. 1 minus 2t squared. I took the 2, so that's 2t, and negative 2t. Okay? So to get the length of this vector, I can simply take the absolute value of this piece and the length of this vector here. Right? So length p prime is equal to, pause for a second. Oh, that's right. Okay. Cool. So then, let's see. I'm going to have this 2 over 2t squared plus 1 squared. And then the length of this, the magnitude of that, is going to be the square root of this squared. And then I've got 4t squared and 4t squared, which is going to be 8t squared, right? Yeah, let's write that out. So I've got 2 over 2t squared plus 1 squared. And then I've got the square root of, this is going to give me 1 minus 4t squared plus 4t to the 4th, right? Now if I add 8t squared to the negative 4t squared, it's just going to give me plus 4t squared, okay? And then that should look familiar from earlier, right? That's the thing that we already factored out. This piece right here equals out to just 2t squared plus 1. So what does that mean? That means this piece wipes out with one of these, and the length of my derivative of the tangent vector here is just the 2 over 2t squared plus 1, this, right? So that's the length right there. And I'm going to divide by that to get my n vector. Well, I've already got it factored out here nice and simple for me. If I'm going to divide by 2, it's going to wipe out that 2. And if I'm going to divide by just a single 2t squared plus 1, it's going to take away one of those as well. So what does that mean? It means that for the n vector, I'm just going to have the 1 minus 2t squared over a single 2t squared plus 1, because one of them wiped out when I divided by the length. Okay, next, 2t over 2t squared plus 1, and lastly, negative 2t over 2t squared plus 1. Okay, so here's my n vector at any point t. right? And I have my t vector at any point t. Right, so I've got my unit, tangent, and normal vectors there. So not horrible, but I did have some quotient rules built in there and a good bit of factoring that I had to do. Let's try using that other method that I was talking to you about with that other formula, right? I showed you that the n was equal to, if I were to do r prime cross r double prime, then cross again with r prime and divide by his own length. And I know what you're thinking. If I cross two vectors that are the same, aren't they supposed to be zero? Yes, but also cross products, multiple of them, do not have an associative property, meaning I can't just switch the order around here, okay? So it's actually not going to come out to be zero even though there's two of the same vector there. We'll just do it in order. R prime cross r double prime will give me a vector, and then I'll cross it again with r prime. Okay, so I've got r prime here. Let's also get r double prime. All right, let's write them out. R prime is 2t squared and 1. R double prime is 2, 4t, and 0. All right, just doing some derivatives there. Okay, let's cross them. R prime cross r double prime is going to give me I, j, and k here. I've got 2t, I've got 2t squared, I've got 1, I've got 2, 4t, and 0. Okay? So then what is that going to be equal to as a vector? Well, if I do the I, right, I'm going to have 0 minus 4t. Then next with the j column, wipe it out, I'll have 2t times 0, which is 0, minus 2, but alternating on the j makes it positive 2. And then for the k right here, I'll have 2t times 4t, right, at squared, minus 4t squared. So I get 4t squared, like so. Okay? Now, if I'm going to do r prime cross r double prime, that thing we just found crossed with r prime again. Okay? So I have my I, j, and k again. I have the negative 4t, the 2, and the 4t squared. And then crossed with r prime, so that's 2t squared, and 1. Okay, so let's do that cross product. If I do my I, right, I'm going to have 2 minus 8t to the 4th. Next, for the j, I'm going to have negative 4t minus 8t to the 3rd, but it's opposite because j is alternating on that one. So I'm going to have 4t plus 8t cubed. And then for the k, right here, I've got negative 8t cubed minus 4t. So I'll write it minus 4t minus 8t cubed so that you can see the similarity there in the last two. And that should give you a hint we're already on the right track, right? Because these two were very identical, right? Just one negative and one positive. All right, so this vector points in the normal direction, right? That's the whole point, pun intended, is after I do those cross products, I get something crossed out that points in the normal direction. So this is already a normal vector. I want the unit normal vector, right? So I need to divide by his length. Let's do some factoring here to make that calculation a bit easier on us. Right? So first of all, the 2 minus 8t to the fourth, I want you to notice that I can pull out a 2, and then it's 1 minus 4t to the fourth. So that's 1 minus 2t squared, 1 plus 2t squared. Next, I can pull out a 4t, 1 plus 2t squared. And last, on this last one, I can pull out a negative 4t, and I get 1 plus 2t squared. Okay? You notice that they have a bunch of stuff in common, right? Okay. So then this is equal to, I can pull out a 2, and I can pull out a 1 plus 2t squared, times the vector 1 minus 2t squared, 2t, and negative 2t, right? That should look familiar, right? There it is, 1 minus 2t squared, 2t, negative 2t. The only thing left to do now is this is still just that normal vector. I just need to divide by his own length, right? Well, we already did that, right? Here's that vector right here, okay? The length of just this portion, okay? The length of just this portion was this, right here, right? Okay. So, my normal vector is going to be equal to 2, 1 plus 2t squared, right? That's this piece, times this vector, 1 minus 2t squared, 2t, minus 2t, divided by the length of this, right? Okay, so the length of this piece is itself, right? And then the length of this portion was another 1 plus 2t squared, right? That was this piece right here. So notice these wipe out, and I'm left with just an over 1 plus 2t squared, right? Which is exactly the same vector as this now. Okay? So I don't know how you feel, whether this was more work or this one. It really just depends on how easy the stuff falls in. But again, I do want to point out the length right here of this thing came out really nice, and it doesn't always have to do that. Okay? Go take a look at what this curve really looks like, and then see what happens at different points on the curve in my GeoGebra.
As I tried to draw pitifully on the board there, you can see it sort of spirals through the center there. Not really spiral, but just really twists through the center there. This is also a non-planar curve. Can't fit into a plane, but it is cool to see the shapes come out. Like you can see in the XY plane that it takes on the shape of one of the root functions. And you can see in the YZ plane take on the cubic or cube root shape, and then in the XZ plane you can see it take on the parabola shape right there. But when you put them all together, you get this cool twisty curve that goes through the origin, right? Okay, so then let's take a look also then from this point right here. That's where t is negative 2.5, right? And basically I'm just letting the point travel along the curve there. So again, just watching the point move along the curve is a little bit deceiving. You don't really see all of what's going on, or whether there's a twist, or whether the the vectors are pointing in which direction. So that's why we calculate the TNB frame. Okay, so look, here's the tangent vector, and then look, it's pointing with the curve. You can see it's basically just on the curve there, right? Which way should the normal vector be pointing, right? It should be pointing in the direction that the curve is turning, like in the curvature's path, right? So if you look very slightly the way this is curving, you should be able to guess which way that unit normal vector should be pointing, right? See, it's curving this way, so it should be pointing into that curvature. And it is. You can see it pointing towards the way the path wants to turn there. Okay, so then you've got your B vector, which is the way that we're going to get any twisting, or in this case especially, since this is a non-planar curve, B is really going to measure the torsion, which is the way that the curve wants to not stay in a single plane, right? You can see the B vector pointing upward, and that is the tendency of this thing to get out of that plane that it's in. So here, let's take a look. Now watch the velocity vector, the tangent vector, really just stay glued to the curve there. And then the other two twist around, right? Because now it needs to be pointing towards the inside of that curvature. The way it twists around there, the B really goes through a lot of changes with the N there as it does that. Let's see that one more time. Watch it twist around. Right? Tangent vector pointing in the direction of the curve, normal vector pointing in the direction that the curve is turning, and then the B vector for the twist.
Here's another example of using things with polynomial pieces in it, and I wanted to bring this one out to show you that it can actually be even messier than that last example. Okay, so let's find T and N this time. I'm going to stop halfway through, or not even halfway, part of the way through the first method, as you'll see that it gets yucky fast. Okay, as a challenge, see if you can finish this way that I'm about to only do part of, and then I'm going to switch over to that other method because it is shorter. So here we go. First thing I want to do, find R prime. So I've got 1, negative 2t, and 3, right? Seems even simpler than the last one, right? Not many things going on here. Well, let's find the length. Right? The length of R prime, square root. 1 squared is 1, 4t squared, and 9, right? So this is a whopping square root of 4t squared plus 10. Good bit yummier than last time, if you get my drift. I'm gonna have to use this as a division in here, which is going to cause some very nasty things that you have to take derivatives of, some of them with quotient rules, and then on top of that you have to deal with factoring out radicals just to do the derivative of that. Okay, so I'm going to leave it right here for you can try it yourself. Go see if you can divide this out, and then that'll be your t, your unit tangent vector. Take the derivative of that, see if you can find n that way. Okay, I'm going to continue with the other method on this one. So I'll need R double prime, which is 0, negative 2, 0. Okay? I'm going to use these two now to find n the alternate way. R prime cross R double prime, I, J, and K. Right? I have 1, negative 2t, and 3, 0, negative 2, 0. So let's find that vector. In my I direction, I have 0, minus negative 6, so 6. And then in my J direction, I have 0, minus 0. Doesn't matter that it's alternating, it's 0. Then in my K direction, I've got negative 2 minus 0. So negative 2, right? If you're not sure that it's at a right angle to both of those other two, double check. Really quickly, if you dot it with this one, you'll see you get all zeros, right? And on this one, really quickly, you'll see you'll get 6 minus 6 plus 0, which is 0, right? So this is definitely still at a right angle to both of those, which incidentally means it should be in the bivector direction, okay? Next, I'm going to do that thing that we just found crossed with the original r prime vector. So I, j, and k. I've got 6, 0, negative 2. And r prime is 1, negative 2t, and 3. So that I get the I direction, I have 0, minus 4t. So minus 4t. In the j direction, I've got 18 plus 2, right? But it's negative. So negative 20. And lastly, I've got, in the k direction, I've got negative 12t minus 0. Right? Okay. So it should still be at a right angle to the original r prime, right? Double check. Negative 4t, negative 40t, and, oh, I'm sorry, positive 40t, yeah, it's positive, and negative 36t does in fact add up to 0. So then all I need is to divide this guy by his own length, right? Okay, well, let's see, we can make that a little bit easier on ourselves. This vector, I can factor a negative 4 out, leaving me with t, 5, and 3t, right? Okay. Then the length here of r prime cross r double prime cross r prime is equal to the absolute value of the 4, and then times the square root of t squared plus 25 plus 9t squared, right? Okay. So now, if I divide this by this, notice the 4, negative 4 over the 4 leaves me with a negative, and then everything in the denominator will have the square root of the 10t squared plus 25. That. Okay. All right. So my n vector is then equal to negative t over square root 10t squared plus 25, negative 5 over square root 10t squared plus 25, and negative 3t over square root 10t squared plus 25. Okay. Now, if you're wondering, where's my t vector, we're supposed to find that too. We already found that, right? The t vector is going to be from my original setup here. I already tested it out to see if I would want to do those derivatives, right? Negative 2t, 4t squared plus 10, and 3 over square root 4t squared plus 10. Okay? So you've already got t, right? It's not too much of an effort ever to get to your unit tangent vector. It's always that extra step that it takes to get to your unit normal vector. Okay? This one is a planar curve, by the way. It's a parabola that follows the plane x equals 3z. right? See, it's a parabola in that plane, right? Pointing away because of the negative. So the plane x equals 3z, slants there, and the parabola is inside of it. Go take a look at it and the frame on points using my GeoGebra.
So this curve is going to be kind of similar to that other one, right? It's just a space curve that's going to just twist around. But this one's a planar curve, okay? It stays in one plane the whole time. It's this parabola right here. Right? You can see the parabola just sticks in this plane. And remember, we already said what the plane was. You can see the straight line portion of it here, right? That's the x equals 3z plane, or I'm sorry, z equals 3x plane, right? I may have said it wrong the last time. Z equals 3x is the plane that it's in there. So anyway, you can see the parabolic shape just because of the squared, and it's negative, so it's pointing towards the negative y axis there. Let me zoom out a good bit here so we can get a better visual on the whole parabola shape there. Right, there it is. The problem with zooming out, though, is these are unit vectors that we're dealing with that I'm about to show, so you may not be able to see them if I zoom out too much. Here's the tangent vector. See, it's just that little bitty tip right there. You can't hardly see it. Let's look at the normal vector. Normal vector should be pointing into the curvature. Right, there it is. Just that little bitty red tip right there. Okay, so let's zoom in a little more so that you can see them. Yeah, there they are. And then, of course, the B vector points in the planar direction there. Okay, now this is a planar curve. So let's see if you can guess what B, the binormal vector, is going to do. Let's go ahead and play it here. Take a look at the way the point's moving there. Of course, the tangent vector is following the curve as it should, and the normal vector is constantly pointing in the direction that the bend is going to pull. Do you notice anything about the B vector, the green vector? Right, let me rewind. Do you notice the green vector, if I line up with the plane, stays perpendicular to that plane the whole time, right? As it should. It's perpendicular to the other two vectors. Okay? So that gives you the indicator right there that you're really not getting any twist. No torsion. No leaving the plane, really, is what it's really not doing. You have that plane right there.
One last example. Wanted to throw this one out at you just to show you what parametric and vector functions can do that normal rectangular coordinates can't. This is an example of a cycloid. Something like if you take a point on a wheel, what kind of path would that point follow as it cycles along the ground, right? So the way I have it set up is this is a curve that follows the plane y equals x. So that's the dotted line that you see basically going along the line in the plane y equals x. Okay? And all it's doing is this, it's just making little trigonometric humps like this, and then it ends in a cusp, and then it does the next hump, right? And then a cusp, and then another hump. And it goes on forever in both directions. Okay? So then we would be interested in finding the t and n, and of course if you were doing more studies, of course you'd find the b also, you'd find the whole TNB frame. But let's just find t and n of this curve. Okay? It's a mixture of polynomial and trig, so you can already expect which way am I going to probably do it, right? The shorter way. So r prime is what? 1 minus cosine t, 1 minus cosine t, and derivative here is going to be sine t, right? Okay, let's do the length. the magnitude of my vector here. So I have square root. These two are the same thing. So I've got 2 of these 1 minus cosine t squares. And I've got plus sine squared there, right? Okay, so then this comes out to be 2 minus 4 cosine t, and then I've got plus 2 cosine squared plus sine squared. Okay, now you can play around with this one a little bit more. You can eventually see that what I've got here is 1 of the cosine squareds plus sine squareds is a 1, plus the 2 gives me a 3. I still have the minus 4 cosine, and I still have 1 of the cosine squares, right? And of course that doesn't factor into a perfect square, so then what you're tempted to do to make your derivatives a little bit easier is maybe complete the square, right? So you end up with something like cosine t minus 2 all squared, and then half of the 4 squared is, half 4 is 2, right? Squared is 4, so you have to do plus 4 minus 4 here, which gives me a minus 1, right? So then from here, there's really not a whole lot else you can do. It's just stuck looking like that. So my t vector is this nasty looking thing. Uh, 1 minus cosine t square root cosine t minus 2 squared minus 1, comma, same thing again, cosine t over square root cosine t minus 2 squared minus 1, and then sine. Okay, so not exactly the epitome of my day of derivatives right there, right? Not going to be a very fun thing to take a derivative of, okay? And as soon as you hit this point, you should see right away, okay, Mr. Simon, let's I'm back off, right? We'll go do it the other way, okay? So let's find n the alternate way. I'm going to start with r prime cross r double prime. ijk, right? I need r double prime in order to do that. You know, if I've been forgetting my vector symbols here, somebody's going to have to call me on that one. Okay, so I've got sine, sine, cosine. That's a lovely one, isn't it? Absolutely. Okay, so I have 1 minus cosine t, 1 minus cosine t, sine t, sine, sine, cosine. Lovely. Okay, so let's do this. Derivative, cross product, not derivative. For I, I'm going to have 1 minus cosine t times cosine t minus sine squared t. So I've got cosine t, because that's cosine times 1, minus cosine squared minus sine squared. So that's just minus 1, right? Minus cosine squared minus sine squared. Gives me negative 1. Okay, so for the j right here, don't forget it's going to be opposite in a minute. I've got 1 minus cosine times cosine again, and then again minus the sine squared. But it is going to be the same result, right? But it's opposite. So I've got 1 minus cosine t. Okay? And then for the k column, I've got 1 minus cosine times sine minus 1 minus cosine times sine. It's the same thing subtracted from itself. So I've got 0. Okay? All right. So now I take that vector and I'm going to cross it again with the original derivative vector. All right, ijk. Need a little more space here for that one. Whoops, nope, that's not more space, David. Okay. Cosine t minus 1, 1 minus cosine t, 0. And then the original other vector here, I've got 1 minus cosine t, 1 minus cosine t, and sine t, right? Yes. Okay. So in my I direction, I've got 1 minus cosine times sine minus 0. Okay? In the j direction, I've got basically the same thing, but just that has a negative on it. But don't forget, the j is alternated, right? So that immediately switches it back to that same exact thing. Sine t, 1 minus cosine t. And then in my k direction, I've got cosine t minus 1 times 1 minus cosine t. That's basically the same thing, right? But one's negative, one's positive. So it's like saying the negative but squared. So negative something squared. Minus 1 minus cosine t, 1 minus cosine t. So what I get is negative 2, because it's the same thing. I'm multiplying this thing minus this thing, right? They are the same thing, but they're both negative. So I get comma, negative 2, 1 minus cosine t squared. Okay? Okay. So that is going to be the vector that points in the normal direction. The only thing left to do is to find the magnitude of that vector. Okay? So let's do that. It's going to be a lovely, lovely thing, isn't it? Okay, so I can make it easy on myself, firstly, by factoring out the 1 minus cosine t. Okay, so 1 minus cosine t times the vector sine, and negative 2, 1 minus cosine. Okay, so then the length of him is equal to the length of absolute value of that, right? But 1 minus cosine t is always positive, right? Because cosine t never gets bigger than 1. So this is always positive right here. So the absolute value of that is just itself. And then the length of that, the magnitude of that, square root of sine squared and sine squared, so I have 2 sine squared, plus 4 times 1 minus cosine all squared. Okay? So let's see, 1 minus cosine t, square root of 2 sine squared, and then I've got 4 minus 8 cosine and plus cosine squared, so plus 4 cosine squared right there. Okay? So definitely we want to interact something with these sine squareds and cosine squareds, don't we? Absolutely. What's going to happen there is I'm going to get 2 sine squared plus 2 of the cosine squareds is going to give me a 2, right? So plus the 4 will give me a 6. Uh, 8 cosine t, still there, the negative 8 cosine t, but now all I have is a 2 cosine squared t. Well, you notice I can factor a 2 out, right? Okay. So I'll do that. Square root of 2 will be out here. This will be 1, 4, and 3. That should look familiar, right? So I'm left with this thing that I could also complete the square on, right? This piece right here. So I have square root of 2, 1 minus cosine t, square root of cosine t minus 2 squared minus 1. This will be the length. Now this, right? This is the length of that vector that I just found. So if I divide this vector, right, this vector here, by this length, right, notice the 1 minus cosine t's will wipe, and I'll just have all of that stuff over square root of 2 times this square root here, right? So my n vector is just sine t over square root of 2 square root of cosine t minus 2 all squared minus 1. Same thing again. Cosine t minus 2 all squared minus 1. And I had negative 2 on that last one. Negative 2, 1 minus cosine t. Cosine t minus 2 all squared minus 1. Okay? So yes, not exactly the most yummiest of all things, but as always, good news. There was a way to do it. There was a way to get a closed form for it. Okay, so I have my t and my n vectors, and at some point, if you were actually doing an analysis on this path, I could very easily cross these and find a b vector, a binormal vector as well. Okay? Go take a look at this curve on your way out.
It is called the cycloid as promised. And you'll notice it does follow the line y equals x, right, through the xy plane there. It is a planar curve, right? It fits on the plane y equals x. But it's a cycloid. It's basically following a point on a wheel, if you will, as the wheel goes around and around through the path. So then, since this is a planar curve, again, you can expect the b vector to be like it is. You'll notice they're all undefined. I'm on a cusp right there at t equals 0. Let me play it a little bit. There we go. So there's your 3 vectors right there again. Let me zoom in a good bit here for a second. Take a look at what happens during one loop of this cycle. Tangent vector follows, right? Follows a path. The normal vector pretty much always pointing down at the center of the curvature there. But then that b vector never turns. It's always pointing outward to the side there. Okay. Now, why would it be undefined at one of these pointy cusp things, you think? Definitely because one or more of our derivatives is not going to be defined at a cusp, right? It's not a continuous derivative there as part of the problem. So we've got a bit of a separation in our function there. Okay. Here, let's follow it one more time. Zoom in. It's a very simple path, you can see. Notice the way the vectors just jumped there for a second. Everything was undefined for a moment, and then all of a sudden redefined. Hence the discontinuity part of the derivatives there. And this thing's going to turn right around. And actually, now it's moving backwards. You can tell it's moving against the flow of the tangent. The computer's just rewinding is basically all it's doing. It's just following a pattern there. And basically, it's just this thing keep repeating over and over again. Right? Now, in case you're wondering, this thing does actually calculate the vectors. It doesn't just put numbers down there. Right? It does actually have all of the t and the length vectors and all the pieces that you should recognize. A little less simplified. The computer doesn't really simplify it as much. But it should be all the pieces there that you recognize, because it's the same set of vectors.